Is it possible to witness on Earth two objects coming together under the force of gravity? And before you comment, yes, obviously it's easy to witness on Earth two objects coming together under the force of gravity if one of those objects is the Earth. But what about just two objects in a room? It turns out it is possible. It's something I've wanted to do for a long time, and I finally got to do it, and it's amazing. The experiment was first conducted by Henry Cavendish in 1797. I wanted to see if I could recreate his setup. And goal one would be to show that two objects in a room can be pulled together by gravity in a way that's visible to the naked eye. And if it goes really well, maybe goal number two can be to calculate the gravitational constant, big G. In Cavendish's setup, there were two weights attached to each end of a bar, suspended by a wire. This forms a twisting pendulum or a torsion pendulum. That's because a wire resists being twisted. So masses suspended in this way will twist back and forth. Cavendish would let that settle and then introduce two stationary masses near these suspended masses. The idea being that the force of gravity would pull the suspended masses towards the stationary masses. If you know the stiffness of the wire, then you can figure out the force of gravity between the masses based on how much the pendulum is twisted from its equilibrium, how much gravity pushes against the force of the torsion pendulum. And the cool thing is, once you've got the force, you can rearrange this famous equation for the force of gravity to calculate the gravitational constant of the universe, big G. I assumed Cavendish's experiment just wouldn't be possible for me to recreate in my studio. It just seems incredibly fiddly. But then I saw this video on the Mr. Lund Science channel, and look, on the time-lapse it's a very clear effect. So I bought some really heavy balls. The stationary masses are wrought iron and they weigh about 14 kilograms each. You need at least one of the masses in an attracting pair to be non-ferrous, either the stationary mass or the suspended mass. That's because you don't want the masses to be attracted to each other by anything except the force of gravity. And if both the balls were ferrous, you would need to worry about magnetism. Like even a tiny bit of magnetism would completely overwhelm the minuscule force of gravity between them. So for the suspended masses, I went with copper, and they're about 5 kilograms each. So here's a time lapse of the suspended masses settling down and finding an equilibrium about which to oscillate. And look what happens when I then introduce the 14 kilogram masses. Absolutely nothing. What? Why not? Mr. Lund got it working. What's wrong with my setup? Maybe I'm doing something differently that just kind of ruins the effect somehow. My first thought was that maybe my wire is too stiff. You can get a sense of how stiff the wire is from how quickly the pendulum oscillates back and forth. A stiffer pendulum will oscillate more quickly, just like how a stiffer spring boing-oings more quickly. But actually, if you look at how long it takes for our two pendulums to make one oscillation, well, they're about the same. That tells me that if Mr. Lund's wire isn't too stiff, then neither is mine. The other difference is like how close can the center of masses get to each other? By my estimation, Mr. Lund's masses, when they're touching, their centers of mass are about 47 millimeters apart. The fact that they are on the ends of a meter ruler makes the calculation from a screenshot much easier. Whereas the distance between the centers of my masses is about double that. And you probably know that the force of gravity goes as the inverse square of distance, so that does have an effect. But even when Mr. Lund's masses are really far apart from each other, you can see the effect. Look, this mass is supposed to be going that way, but it just stops dead, turns round and goes towards the lead block. And then I thought, well, hold on a second, we actually do know the value of big G. So given the parameters of the experiment, we should be able to calculate roughly how much we expect that pendulum to twist around towards those stationary masses. In other words, we should be able to figure out to what extent is the force of gravity able to overcome the stiffness of the wire. And just to be clear, because the pendulum is always oscillating, we're really talking about how much does the equilibrium position of that oscillation move when the stationary masses are introduced. Instead of going into the derivation of the equation, I'll leave a link to a video that does that quite nicely. So here's the equation for big G that you can get from the Cavendish experiment, where L is the length of the rod separating the suspended masses, R is the distance between the centers of mass of the two masses in the deflection position, M is the mass of the stationary mass, theta is an angle, It's how much the pendulum moves when the stationary masses are introduced, and t is the time taken for the pendulum to make one oscillation. That's there representing the stiffness of the wire. Side note, you'll notice that the mass of the copper balls doesn't come into the equation, and actually that's something we should expect in the same way that the rate at which an object accelerates towards the Earth is independent of the mass of the object. It's always 9.8 meters per second per second. One consequence of that is I could have used much lighter hanging masses, which would have meant I could have used thinner wire without it snapping, which would have made the experiment more sensitive. But anyway, because we know big G, we can rearrange this equation to find what theta should be. And when you plug it all in for my experiment, we should expect a deflection of only about 0.1 degrees. And in fact, you expect roughly the same amount for Mr. Lund's experiment. And that was at first confusing and then disheartening. Confusing because, well, look, this is what 0.1 degrees looks like. You can barely see that there's an angle there with the naked eye. You'd certainly be hard-pressed to see a change like that in the experimental setup that I have here. And although the suspended masses in Mr. Lund's experiment never actually reach their new equilibrium position because they collide with the stationary masses first, it's still clear that the deflection is much greater than 0.1 degrees. Could there be something else in this video that's attracting the masses towards each other? The stationary masses are made of lead, so it can't be magnetism because lead isn't ferromagnetic. Could it be electric charges attracting each other? Well, I did some rough calculations, and it seems as though you could get a force of attraction greater than the force of gravity from a charge that is less than the amount of charge you typically get from a static electric shock. So maybe that's what's going on. Maybe some charge was transferred to the masses inadvertently. But then again, that assumes that the two masses have an opposite charge to each other, which seems like an unlikely thing to happen. Like if you've got one charged object and one uncharged object, they'll still be attracted to each other because the uncharged object becomes polarized by the charged object, but that's a smaller force. But generally it was difficult to find good quality information about like what is the typical amount of charge you might find on a lump of metal in everyday life. So I'm not convinced by that idea at all. I'm really grateful to Mr. Lund actually for helping me think through all this stuff. He was tempted to take his video down because it wasn't quantitative, it was just qualitative. But after speaking to a professor who was convinced that it did indeed show the force of gravity, he decided to keep it up because people were using it as an educational aid. But anyway, assuming my calculations are right and the expected deflection is just a fraction of a degree, then I made this whole setup for nothing. But Steve, you promised us at the start of this video that we would see two masses in a room moving towards each other under the force of gravity. I did, and you will, thanks to Simon Foster at Imperial College London, because it just so happens that they have this beautiful lab bench example of the Cavendish experiment. It's much smaller than my setup, but it's also much more precise, and it has some really clever features. You've got the long wire thread coming down here, and you see it coming down there. You also have to spend ages making sure that the hanging masses are centered enough that they won't bash into the insides of the container when you introduce the stationary masses, which took another couple of hours. And then look, these stationary masses, they're actually movable. So first you put the masses in this position and you wait for the hanging masses to settle down. Then you swing the stationary masses around to the other side and then let the hanging masses settle again. But this is the really clever part. How do you measure theta? How do you measure the change in angle of the hanging masses due to being pulled one way and then the other by the stationary masses? Well, just here on the wire there's a little mirror, and you can see here we also have a laser pointer. So look, with the laser pointing at the mirror, you can see the reflection on the wall there, and of course the reflection is moving back and forth as this torsion pendulum that is the hanging masses oscillates side to side. In the time-lapse you can even see, look, it's settling down. By the way, each full oscillation is about 10 minutes long. That's one of the ways that this instrument is more sensitive than mine. That longer oscillation period tells us that there is a much smaller restoring force from the twisting wire, meaning the position of the hanging masses will be more affected by the gravity of the stationary masses. It also means that this whole thing takes a heck of a long time. So I hope you'll forgive me for, at this point, deciding that the equilibrium position is about here, marked in green. So then we switch the stationary masses over to the other side, and in doing so we disturb the apparatus a little bit and set the pendulum oscillating again. And once again, here it is settling down in the time-lapse. And eventually you can see that the new equilibrium position is different to the old one. How cool is that? we have witnessed gravity acting on objects in a room. And look, after I got bored, I decided that the new equilibrium position was about here. And I measured the distance between the equilibrium positions and some other distances and the period of oscillation and put them all into this equation. You'll notice this is very similar to the equation we saw before. The only difference is that theta has been replaced with this term here. That's just the distance that the laser point was deflected by, divided by the distance from the screen to the apparatus. And if we make the small angle approximation, that value is theta. But you also have to divide by 2 because the deflection of the laser is always going to be twice the deflection of the mirror. I could cancel out the 2's, but I wanted to show you what was going on. And I get a value for big G of 7.4 times 10 to the minus 11. And hey, here's the real value of G. That's not bad, is it? I just measured big G in the lab and it wasn't terrible. I always thought I was a bad experimentalist, but maybe after years of struggling to get things working for YouTube videos, I'm not so bad at it anymore. Or maybe it was just a fluke. I don't know if this is weird or not, but as a kid, I used to do these mathematics workbooks in my spare time. Like my dad would bring home these problem books and I just absolutely devoured them at the weekends. And I really think it made a difference actually, because, well, it's well known that you learn better through doing something than through passively taking in information. So what about the contents of this video? If you want a fun and easy way to learn about gravity and then retain what you've learned, I highly recommend the sponsor of this video, Brilliant. Brilliant is really interactive, so you're fully engaged. And actually now it's the thing that I do on my phone when I would normally be playing a game because it's really fun. And it's the best way to learn about mathematics, science, data science, and computer science. Brilliant has thousands of lessons all the way from basic up to advanced, and new lessons are added every month. Because it works on phones and tablets as well as laptops and desktops, it's easy to commit to 15 minutes a day, build up this habit for learning. And before long, you're mastering these big concepts. And it's customized to your skill level. You don't move on to the next level until you're really happy with the previous level. As well as the course on gravitation, one that I really like is the Thinking in Code course. It just really tickles that problem-solving part of my brain, and I'm learning a really useful skill along the way. The great thing is you can try everything that Brilliant has to offer for free for a full 30 days. Go to brilliant.org/Steve Mould. The first 200 people will get 20% off Brilliant's annual premium subscription. The link is also in the description, so check out Brilliant today. I hope you enjoyed this video. If you did, don't forget to hit subscribe, and the algorithm thinks you'll enjoy this video next.